Good morning everyone. I am Prasanna Kumar from CSM department section C and today I'll be presenting on a method of crystal plasticity finite element modeling in BCC, FCC and HCP metals from engineering physics course. This topic lies at the intersection of materials in this topic lies at the intersection of material science and computational mechanics, focusing on how we can model and predict the deformation behavior of crystalline metals. Introduction to Crystal Plasticity Finite Element Modeling. Crystal Plasticity Finite Element Modeling or CPFEM is a numerical method used to stimulate how individual crystals in metals deform under mechanical loads. It combines crystal plasticity theory, which describes deformation at the gain or crystal level, with finite element analysis, which solves large scale stress strain problems. This integration helps engineers predict how metals behave under different conditions, which is crucial for designing stronger and reliable materials. Importance of crystal plasticity in material source science. Crystal plasticity is important because it helps us understand anisotropy, the directional dependence of material properties. Real metals aren't perfectly uniform. Their properties change with direction because of how atoms are arranged. By modeling crystal plasticity, scientists can predict mechanical behavior more accurately, optimize manufacturing processes, and design new alloys with desired strength and ductility. Ultimately, this modeling improves performances and durability in engineering applications like aerospace, automotive, and nuclear materials. Overview of crystallographic structures. Metals mainly crystallize in three structures: BCC, that is body centered cubic, examples like iron, chromium; FCC, that is face centered cubic, examples are aluminium, copper; HCP, that is hexagonal closed packing, examples titanium, magnesium. Each structure has different slip systems, which are preferred planes and directions where deformation occurs. For instance, BCC metals have fewer active slip systems at low temperatures, while FCC metals have many, making them more ductile. The atomic arrangement strongly influences how easily a material deforms. Fundamental of crystal plasticity theory. Crystal plasticity theory describes how individual grains deform through slip and twinning. It relies on constitutive equations that relate the applied stress to slip rates on various crystallographic planes. The model accounts for the orientation of each grain, the active slip systems, and hardening laws that control resisting to deformation. By modeling these mechanics, we can understand plastic flow at the micro scale and predict macroscopic material behavior. Finite element method in crystal plasticity. The finite element method FEM divides a complex material domain into smaller elements, allowing detailed analysis of stress and strains. When combined with crystal plasticity, FEM can stimulate how each grain in polycrystalline material behaves under load. This coupling helps capture local variations in stress, strain, and slip, providing a micro level understanding of deformation that traditional models cannot achieve. Constitutive models for BCC metals. BCC metals exhibit distinct slip behavior primarily on systems with temperature dependent activity. The model accounts for the higher Pearl's barrier and thermally activated slip mechanisms. Hardening laws and rate sensitivity are tailored to reflect BCC dislocation mobility characteristics. BCC metals such as iron or tungsten have unique deformation behavior. They deform primarily on slip systems, but their slip activity is temperature dependent due to a high Peirce barrier, meaning dislocations need more energy to move. At higher temperatures, deformation becomes easy. The constitutive model includes thermally activated slip mechanisms and specific hardening laws to accurately represent BCC plasticity. Constitutive models for FCC metals. FCC metals primarily deform via slip systems enabling easier plastic deformation. The model incorporates multiple slip systems and considers cross slip and stacking fault energy effects. Hardening behavior includes rapid initial slip activity followed by saturation due to dislocation interactions. In FCC metals like in, in FCC metals like copper or aluminum, deformation mainly occurs on slip systems. These metals are highly ductile because they have many available slip systems. The model also considers cross slip where dislocations move from one slip plane to another and stacking fault energy which affects how easily dislocations move. Initially deformation happens quickly but then saturates as dislocations interact and harden the material. Constitutive models for HCP metals. HCP metals demonstrate limited slip systems often involving basal, prismatic and pyramidal planes. Twinning and slip are both effective deformation mechanisms, especially at different temperature regimes. The model integrates the influence of crystallographic texture and anisotropic hardening effects. HCP metals such as titanium or magnesium have a more complex deformation behavior due to their limited slip systems. Here, both slip and twinning are crucial for plasticity. Different planes, basal, prismatic, and pyramidal, becomes active depending on temperature and stress. The model includes the influence of texture and anisotropic hardening, which are key to predicting the deformation of HCP metals accurately. Numerical implementation of the method. The crystal plasticity model is integrated into the finite element framework through incremental stress strain updates. Numerical algorithms handle the nonlinearities arising from slip system interactions and hardening. Convergence criteria ensure Convergence criteria ensure accurate systems during large deformation similarities. The CPFEM is implemented in the finite element framework through incremental updates of stress and strain at each element of because of because of non-linear interactions among slip systems and hardening behavior. Numerical algorithms must be robust and interactive. Convergence criteria ensure that the stimulation remains accurate even under large deformations. This step essentially connects theoretical crystal plasticity equations with computational simulation. Calibration and validation of the model. Calibration involves determining material parameters using experimental data such as single crystal stress strain tests. Validation checks whether the model can reproduce observed deformation patterns in real materials. Additionally, sensitivity analysis helps identify which parameters most influence the model's predictions. This process ensures that the CPFEM remains both accurate and reliable for different metals. Applications of the method. The method predicts the evolution of microstructure and structure texture during forming process. This it aids in understanding failure mechanisms like crack initiation and propagation in crystalline metals. The approach supports the design of new alloys with enhanced mechanical properties. This modeling method is widely used in material engineering. Applications include predicting microstructural evolution during forming or rolling, understanding crack initiation and propagation, and designing new high performance alloys. By visualizing slip and stress at the micro level, engineering can better prevent failure and optimize the manufacturing process. Advantages and limitations. The model provides detailed insights into microstructural deformation mechanisms at the grain level. It computational cost can hide due to the complex constitutive equations and microstructure resolution. Simplifications are often necessary for large-scale simulations without sacrificing without sacrificing critical accuracy. Future directions in crystal plasticity modeling, incorporating effects of grain boundaries, phase transformations, and temperature dependent behavior, developing multi-scale models that connect atomic scale mechanisms with macroscopic responses, improving computational efficiency through advanced algorithms and high performance computing. Summary and conclusions. The presented method effectively models plastic deformation in BCC, FCC, and HCP metals at the crystal level. It offers valuable insights into anisotropic behavior, slip activity, and microstructural evolution. Continued development will enhance predictive capabilities for complex engineering applications. Thank you for your attention. I hope this presentation has provided insight into how crystal plasticity finite elements modeling contributes to understanding and improving metallic materials. Thank you.